So I, on the last minute, decided to actually add some new content. So those of you who have heard this talk before, you might actually hear something new. But as a result, I may push up against time. So anyway, I'll be talking about Roman and the Roman Galactic Exoplanet Survey. Um, all right. So we've seen various versions of this plot before. So this is just showing planet mass as a function of period for known exoplanets color-coded by the discovery technique. This is from a paper by Wei-Cheng Zhang that came out earlier this year. I just want you to notice a few things about this. One is that this bottom right region of the parameter space is pretty much empty. And that means our census of exoplanets is incomplete. The second thing to notice is that that area actually encompasses most of the analogs to our solar system. Third, you can see that the exception there is of course the microlensing detections that probe that region of parameter space. Although, as I'll argue, the full power of microlensing requires a space telescope. And then the last thing, which you can't see from this, but you can see from this little cartoon, which is showing the location of the known exoplanets in the that we know of relative to a kind of cartoon of our galaxy. That most of the exoplanets we know of are are relatively local to the sun, and in those that are somewhat far away. Are mostly in the thin disk from Kepler. The exception, of course, is this kind of plume of detections there, and those are, of course, the microlensing detections. So microlensing is essential for trying to complete the census of exoplanets. And you can come up with all sorts of great theoretical reasons why you would want to complete the census. So we've heard about the snow line. So planet formation is likely more efficient beyond the snow line. It might be where most giant planets form. We would like to survey that region over a broad mass range, broader than the range of masses we can probe now with direct imaging and radial velocities and ground-based microlensing, so we can answer questions like, how do embryos grow or planets grow from embryos to giant planets? What are ice giants? Are they just failed gas giant planets? And what lives out there? Is it just a bunch of failed gas giants? Is it a single gas giant or multiple gas giants like our solar system? The region beyond the snow line is likely the source of water for habitable planets. So if you care about habitability, you want to know how that water gets delivered to the habitable zone, because there's this paradox that we have that the location of the habitable zone is generally inside the water ice line in the protoplanetary disk. So the stuff that you make habitable planets with is probably dry. And then finally, elemental abundance, as in particular things like alpha to Fe will vary as a function of your host star properties. And right now we're mainly just probing things in the thin disk, which have a very relatively narrow range of metallicities and alpha abundances. So we would like to understand how planet occurrence is affected by alpha abundance, for example, and that probably impacts habitability as well. Okay, so those are all really great theoretical reasons. That's not the real reason I think we should do it. The real reason I think we should do it is because anytime we open up a new region of parameter space in this field, we are surprised. So microlensing is, so those of you that are converts will know all this. Those of you that are not, my job is to convert you. So microlensing is sensitive to planets beyond the snow line. That makes it complementary to other techniques. It's sensitive to extremely low mass planets, all the way down to 10% the mass of Mars, maybe even lower in some cases. Long period planets, including ice giant analogs. As far as I know, this is the only technique to detect mature ice giant analogs. Perhaps you can detect young ice giant analogs in protoplanetary disks. We'll talk about that briefly at the end of this. You're sensitive to planets orbiting pretty much anything that happens to float along your line of sight, the background stars. So that could be M dwarfs. And a lot of people in the exoplanet community have gotten it in their heads that microlensing is only sensitive to planets around M dwarfs. That's partially our fault because we spent a lot of time hyping that up early on because we thought that was a niche that we could advertise. But unfortunately, we did too good of a job, and so people have now kind of gotten that stuck in their head that we're only sensitive to M dwarfs hosts, and that's not true. We're sensitive to everything, brown dwarfs, FGK, main sequence stars, white dwarfs, neutron stars, and black holes should they host planets. The typical mass is typically, somewhere in the M dwarf regime, but there's still sensitivity to other kinds of host stars. We're sensitive to free-floating planets. I know you're shocked by that. You haven't heard that yet. Giant moons, including Earth-moon analogs, multi-planet systems, analogs of our own solar system, wide circumbinary planets. So we've detected a few, one clear wide circumbinary planet and a few other candidates, I would say, where the interpretation is ambiguous, but we should detect a lot of them with Roman. Outer habitable zone planets, and then planets throughout the galaxy, including planets in the thin disk, thick disk, and bulge populations. So in principle, we can probe planet frequency as a function of alpha to Fe, although measuring those parameters in the individual host stars will be challenging. Okay, so what is Roman? Roman is not the Roman Empire. It is Nancy Grace Roman. So Nancy Grace Roman is pictured here. She served as NASA's first chief of astronomy throughout the 1960s and 70s. She was instrumental in getting Hubble off the ground, and so for that reason, she's often called the mother of Hubble. So we were quite happy to have this mission named after her. Okay, so what is Roman? It is basically Hubble in terms of its aperture, in terms of its wavelength range, 0.5 to 2 microns. And in terms of its resolution, obviously it's similar to Hubble because of the same wavelength and aperture. Some key differences are that it will be operating at L2. That's really important. It's a nice, quiet, stable environment that you can look at places in the sky for long periods of time. And of course, it has a very large field of view, 0.281 square degrees. It has 7 filter imaging. I won't have too much time to talk about that. We're going to focus on a wide filter between 1 and 2 microns with the Raman Galactic Bulge Time Domain Survey. It also has 2 dispersing elements, low resolution, which may be useful for the bulge, although that has not been really worked on very much. It also has a chronograph instrument, which is not really that relevant to this particular conference, but is really important for doing technology demonstration for the Habitable Worlds Observatory. So that'll be really exciting to see what it does. Okay, so the way Roman achieves this large field of view is by using 18 H4RG detectors in this kind of smiley face configuration or frowny face, depending on which orientation you're looking at. And so this is 100 times the field of view of the largest instrument on JWST or HST. But not just that, Roman also is much more efficient telescope, so it has 1,000 times the sky mapping speed, which means you can map large areas of the sky relatively quickly or smaller areas of the sky at high cadence, which is, of course, what we're interested in here. Okay, so Roman is real. A lot of people sort of have not actually caught up to this. This is just some pictures of various pieces of Roman here that you can see at the Goddard High Bay. But more importantly than that, all these pieces are now together. This is a subset of the Roman telescope called the SCIPA, which contains the optical assembly and the instruments. It was put into a very, very large vacuum chamber earlier this year and was tested for many months and basically passed all of its tests. There was a few surprises, which they are not showstoppers, things that can be fixed. And now it has been lifted out of that container and assembled. So you can see here the outer barrel assembly being put on top of that SCIPA, and then these are the solar panels. So Roman is now complete. It is now a whole observatory. It will undergo a few more tests, and then it is going to be shipped out to Cape Canaveral sort of mid-summer next year, and it is on track for an October 2026 launch date. Now, I've been showing this slide for 3 years, and the only thing that's changed is recently This has been moved to September. So we are ahead of schedule. And people ask me about the budget and the impact of the shutdown. The impact of the shutdown seems to be basically negligible so far. The impact of the budget, we will wait and see. But currently, if either the House or the Senate budget goes through, we should be fine. So we're not worried about that, and they are planning. They're accelerating the schedule and have been accelerating the schedule to try to launch early, because if you launch early, you save money. Okay, so Roman is going to do lots of cosmology. Great, but we're going to focus here on the Roman Galactic Bulge Time Domain Survey. So this is about 1.7 square degrees towards the bulge, a 438-day survey. So it's about 8.5 full moons in size, which is relatively modest, but still a large area. This is the parameters, which are now basically finalized for the Galactic Bulge Time Domain Survey. These have changed. If you haven't looked at this in a year or so, they're now different. We now have 5 main fields and then 1 galactic center field, which is very exciting. 1.5 degrees. The wide filter is going to be the main filter that we use. That's going to be 12-minute cadence. This is down from 15, which was the notional survey before. 67 exposures, so those are longer exposures than before. Observations every 3 hours, and secondary filters, F087 and F219 are the 2 secondary filters, and there'll be 6 72-day seasons, 3 in the beginning and 3 at the end of the 5-year mission. Those will have about 98% efficiency. There'll be some time for momentum dumps and supernova observations and things like that. There's going to be a total of about 50,000 exposures in the wide filter, again, over that 438 days. This will be one of the longest exposures of the sky ever taken in these wavelengths. This is a simulated image from Matthew Penny of what the survey might look like. There are millions of stars in this image, and this is 0.7% of the survey area. So multiply this by about 150, and that's the survey area you can imagine. So imagine, tiling this entire room with these kinds of images, and you still wouldn't have the whole survey. So this is a lot of data, and there's a lot of stars, and of course that's what we need for microlensing because it's rare. So Matthew has really been done the majority of the lion's share of the work in trying to figure out what the survey could detect, and the optimal survey strategy. We all owe Matthew a huge round of applause for all the work he's been doing. But here are some simulations, some simulated light curves from his simulation tools. And on the left is a detection of a Ganymede mass planet at 5.2 AU, and the one on the right is a free-floating Mars mass planet. If you're not familiar with microlensing signals, they are large and highly significant. So it's 27 sigma, 23 sigma. These are not, you cannot explain these with statistical fluctuations. The systematics should be controlled at a much better level. And by and large, there are no false positives that we are worried about, with a caveat, which I'll get to in a minute. Okay, so the yields are large. I think that's the main point you should take away from that. So the updated yields are being done by Farzana, a graduate student at LSU. We'll get those soon. The bottom line is that, though, you really shouldn't believe these numbers, because if we knew the answer, we wouldn't have to do it. But nevertheless, we will have large samples with which to do good statistics. That's the point, including sensitivity all the way down to very low mass planets. Okay, so there's lots of cool stuff, as Etienne mentioned, that we can detect with Roman. We're going to probe new regions of parameter space that we can't do with ground-based surveys. So this is just a sort of smattering of ideas of what we might be able to do with Roman and various people that are working on it. Potentially habitable planets, so we might be able to constrain A to Earth. Circumbinary planets, we should detect those, wide circumbinary planets. Moons, the yield is not high, but maybe if we get lucky. Solar system analogs, planets orbiting brown dwarf and remnants has not even been looked at very carefully. So there's a lot that we can do, but here we're focused on free-floating planets. So we'll focus on those. I just want to mention that the statistical power of the Roman Galactic Bulge Time Domain Survey is enormous. So for a typical sort of 21st magnitude star in the wide filter, you get a 1% photometric accuracy per point per epoch and a 1 milliarc second astrometric accuracy per epoch. And of course, you have something like 50,000 of those exposures. Sorry, this is an old version of this. It should be 50,000. So if you can really harness that root N, you can do a lot of stuff. So just as an example, we should have the photon noise to measure the parallax of stars all the way to the galactic bulge to 10 sigma. Just from the astrometry alone. That's if we can control our systematics, which is a big if, but we're optimistic. Okay, and of course, you'll do this for a ton of stars. So down to this 21st magnitude, you'll get something like 40 million stars. And this is from the old survey, so it'll be a little bit different, but not a lot. So that's just when you have that many stars, that many epochs, that high of precision, that good control of systematics, because we're in space. The things you could do are amazing. Just to give you a sense, there's tens of thousands of microlensing events that will be detected with this survey. Okay, so one thing you can do is you can detect transiting planets. So, the per point photometric precision is generally not good enough to detect a transit, and the cadence is not great, but you can just fold the light curves over your 438 days and you can build up statistics and signal to noise very easily. This is how many transit surveys are done. And so you can easily detect Jupiter-sized planets around a ton of stars, almost 100 million stars. But you can even detect lower mass planets, so smaller sized planets around some stars. So these are yields done by Robbie Wilson at Goddard Space Flight Center. I couldn't actually find a picture of him online, but those of you that know him, he's a kind of redheaded, bearded guy. You'll recognize him. He's very jolly. Anyway, he's also extremely talented, and so he's done these very great simulations of the transiting exoplanet yield. And so this is showing the yield as a function of the distance to the host star, broken up by the size of the planet, the spectral type of the host star, and then the galactic population. And so you can see here the numbers here are large. And you can see that we're probing all of this range of radii for the planets, spectral types, and all major stellar populations in the galaxy, except for the halo of the galaxy. You'll only be able to detect about these small planets around sort of 5 or 10% of the stars, but 5 or 10% of the yield, which is 100,000 transiting planets, is still a very large sample, larger than all the planets that have been detected by Kepler. Now, following these up and getting rid of false positives, that's an entire different talk. It's hard. I think we can do it. I have ideas. Other people have even more clever ideas, but anyway, I think we can do it. And if you combine the sensitivity of the microlensing and the transit survey, I say those of you have probably seen the penny plot many times. This is the updated plot, now including the transiting planets. And you can see that Roman will be sensitive to all planets with mass/radii greater than twice that of Earth, from separations from 0 to infinity over all major stellar populations in the Milky Way over a very broad range of spectral types. So this will, and that of course includes free-floating planets. So this will be in some sense the ultimate demographic survey of exoplanets that we can use to test our models. Okay, so that's kind of the end of my usual talk. So this is the new part. We'll see how it goes. I like to think of, well, this part isn't quite new, but anyway, I like to think of the motivation for why we would want to understand why planet formation is hard is because if you believe in a bottom-up planet formation scenario, and Eugene Chang, if you were at the meeting last week, mentioned this, bottom-up is the hardest way to understand planet formation because you have to understand the physical processes by which the micron-sized dust grains, which condense out of protoplanetary disks, grow by some 13 to 14 orders of magnitude in size or 38 and 41 orders of magnitude mass to get to the mature planets that we see today. And as you you move through all those orders of magnitude, the physics that governs how things stick together changes dramatically. And I think that's kind of the fundamental reason why planet formation is hard. But we're offered an opportunity with Roman to measure the sort of whole population of bound and free-floating planets. And in this sense, this provides sort of an integral constraint on planet formation. And this is an argument that I first heard from Matthew Penny, and I think is a really elegant idea. And that, because of this, we can actually measure the efficiency of planet formation in a quasi-independent way, or quasi-modeled independent way. So, you can think of it this way, and this is nothing, there's no physics in what I'm about to show you, but basically, you have the mass of your disk that's going to form planets. So some of this will form condensed objects. I just call them that for, I don't know what else to call them, but planets, comets, anything that condenses is self-gravitating. Then you have stuff that accretes onto the star, and then you have stuff that gets blown out of the system through photoevaporation or radiation pressure or whatever, right? And those things have to equal the mass in the disk. And so, you can sum this up over all of your stars, and then you have now an integral constraint on the mass of the disk, the mass of the stuff that forms self-gravitating objects, plus the mass that's lost due to accretion and evaporation. It has to be equal to the mass that you started off with. And so in principle, we can measure this total mass of condensed objects with Roman and divide that by the total disk mass, and we measure in some sense the efficiency of planet formation. And the nice thing about Roman is we can do this for both the bound planets and the ejected planets, the free-floating planets itself. Now, there's some caveats to this. Obviously, we have to be able to distinguish things that form as stars, because those we might add those onto our ejected mass when they in fact don't count in this accounting. But anyway, I think this is this provides a very interesting sort of broad constraint on planet formation. Okay, so what are the yields of free-floating planets? So they're basically large. So this was done by Sampson Johnson since left the field. These are the yields for a log uniform distribution of planets. You can see that it starts to die pretty quickly here around moon mass things. But remember, the Sumi et al. Frequencies are large and go up as mass to the -1. So this is the number of stars per dex. Number of planets per free-floating planets per star per dex from the Sumi. So if you multiply these two numbers together, this is what you get, and you can get a large number of free-floating planet detections. Taka did this more correctly in his paper. These are the numbers he gets. So about 1,000 planets down to the mass of Mars. I don't think this is a very big extrapolation from where there are actually detections. There's lots of uncertainties, of course, which are reflected in these error bars. But anyway, the bottom line is that there's a lot of planets. We should detect, if these numbers are right, anywhere between one planet every 10 or to one planet every 35 hours in the Roman survey. In this plot, which shows the total mass in free-floating planets as a function of the mass of the planet, the Sumi, because it goes as mass to the -1, it has equal amount of mass per dex in stuff. Per dex of mass of the object. So it's flat in this curve. So in principle, if the central value of the Sumi mass function is correct, we should detect free-floating planets all the way down to Pluto, which would be very exciting. Okay. There's another thing that we can detect, which is analogs of the gap opening planets. So people that may not be familiar with this, this is a 10-year-old result now, but anyway, ALMA looked at protoplanetary disks and found lots of things with gaps. And these gaps could be due to any number of things, but one hypothesis is that they're due to planets. Each planet has a gap. You can estimate the mass of the gap if you assume something about the viscosity of the disk. And then you can estimate masses, and you can put them on this plot. And here you go. There's a bunch of things like there. And so these would be analogs to the ice giants in some sense. Microlensing would detect these as free-floating planets. So all of these would appear as free-floating planets. And Yi and Kenyon showed that everything with mass above here would actually violate the constraints from the SUMI, the MOA, and KMT net free-floating planet yields. So these all can't be planets, is the bottom line, or at least not planets of these mass. Now, other people would argue that they could be much lower mass if your viscosity is very low. If you have an inviscid disk, then it doesn't take very much to open up a gap. Anyway, we can probe that really well with Roman. Okay, so there's some challenges with Roman. This was already shown. Michelle Kunimoto and Will DeRocco and other people did a search in TESS over 5 sectors looking for free-floating planet candidates. They found this particular example, which is kind of semi-famous now, which looks very much like a free-floating planet event. It is very well fit by a PSPL event. It is much more well fit by a PSPL event than any kind of flare event. It has theta E and TE inferred that are consistent with what you'd expect, a half solar mass or half Earth mass planet at 700 parsecs, moving at a reasonable velocity. The first argument for why this couldn't be a microlensing planet was that it was unlikely. It's actually not that unlikely. If you take the SUMI mass function and go to the +1 sigma upper limit to the upper limit to the slope, you find that it's probably likely that you would have detected one in these 5 sectors. If you do the central value, it's a 7% chance. So it's not really that unlikely. I need to wrap up. Yeah, I knew it was going to be too long. But anyway, but as was mentioned, that the variability, out of baseline variability is significant. So that suggests that this is an active star. Maybe that's why it's flaring. The problem with the flare interpretation is that it requires an energy that is enormous, 2 orders of magnitude larger than all the flares that have been quantified by the TESS in the TESS sectors. So if this is a flare, it is a very unusual flare. All right. Okay, I will skip that. Let me just go to, because that was all said. This is a great time, just to remind you that all the data will be non-proprietary. So that means that anyone can analyze it. If you're new to microlensing, this is a great opportunity. If you love transiting planets, there's a lot of planets to analyze. The Cycle 1 call for proposals just came out a few days ago. They're due March 17th. If you want to know about it, you can ask me, or you can just go look it up online. There will be funding for analyzing data that comes from the surveys that are already planned, but there's also plans. There's also an opportunity to apply for new time as well. There will be not very many other calls, so take advantage of this opportunity while you can. If you want to learn more about our infrastructure team, you can look at this QR code, which I'm happy to share these slides with anyone. And then I just want to finally end by saying that we are initiating a microlensing data challenge, which will start in January. The QR code for it is here if you want to find information about it, or you can look on our webpage. And the goal is to sort of try to get people involved with analyzing microlensing, and we'll provide a tutorial. There's a workshop during the AAS meeting in Phoenix that you can join if you'd like, but you don't have to. And we'll provide tools to help you. Tools to help you get involved. All right, and I'll just stop there.
Thank you, Scott. Any quick questions?
Yeah, I had a comment about the very unusual flare. In our 2012 paper on short duration events, we had one event that looked like a wide orbit bound planet with not very many observations. And Udalski pointed out that the star located at was pretty red, like a foreground M4 dwarf, and so we talked to some flare experts, and what's the probability of seeing a 1 magnitude flare on white light flare? And it's very unlikely. Once every 400 years, which of course made us think, well, that's really likely compared to microlensing. And so it's clearly that's what the signal was. And I think, the point is that the flares are a lot more common in microlensing events. So, we have to be concerned about the very unlikely flares because they're still going to be more common than microlensing events.
I agree, but if you say that this is a flare, then the rate of this flare is almost equal to the rate of microlensing you expect in TESS, right? We expect basically one TESS event, and we saw one flare event, which is so. It's as unlikely as microlensing in this particular case at the 1 sigma Sumi mass function.
Okay.
I'm not saying it's not a flare. I'm just saying it's a really weird flare if it's a flare. I just, that's all I'm saying.
Good question.
Cool talk. Did I hear you right that it's going to be 100,000 transiting planets possibly? And what are the cool ideas for following that up for getting rid of false positives and stuff?
Yeah. So my thinking on this is several-fold. One is that there will be a subset of them that will be bright enough that you can get radial velocities, or you can do follow-up light curves, those kinds of things. So you could determine the rate of false positives from that. I think the real answer to this is that you have to do a global forward model of the entire population of planets and eclipsing binaries that are the main source of false positives, and then use a statistical analysis to distinguish between the two of them, calibrated by the few that you can do follow-up. There's other ways to get rid of false positives. We'll detect secondary eclipses in a number of these things. Some of them will have ellipsoidal variability. I'm not an expert in this, but there are ways to deal with it. It's hard.
Okay, we'll have to move on. Sorry. So thanks, Scott, again.